Welcome. Over the past 8 or 9 lectures, we have seen many aspects related to thermodynamic properties of pure fluids. It might be worthwhile reviewing whatever we have seen so far, so that the learning is better. Let us spend today in reviewing the thermodynamic properties of pure fluids that we have covered so far. We first looked at what a fluid was. It is either a gas or a liquid, that we all know, and then we said we were going to look at easy to measure thermodynamic properties, which are essentially PVT of gases. Then we said we would extend it as appropriate to liquids, first gases and then to liquids, and then we said that we would express the other thermodynamic properties such as internal energy and entropy, enthalpy, Helmholtz free energy and Gibbs free energy, as well as let us say fugacity coefficient, in terms of the more easily measurable P, V and T. That was the whole scheme of things for this module, and we first looked at an ideal gas, which you are already familiar with from your earlier classes. So, we will not spend much time on that. We know that the relationship between PV and T for an ideal gas is PV equals RT for 1 mole of an ideal gas, or molar volume considered here, and this results when there are no interactions between the molecules of the gas. That is when a gas would be ideal, and it so happens some gases, some noble gases, do follow the equation of state for ideal gas. This is called an equation of state. Any relationship between PV and T is an equation of state, and this is where we brought in the things specific to our course. We said in terms of the chemical potential, we will define or we have already defined the ideal gas as something that follows mu equals mu naught plus RT ln P. In fact, we have defined what a chemical potential is earlier. We are defining what an ideal gas is in terms of the chemical potential in this module. We said mu equals mu naught plus RT ln P, one that satisfies this equation is an ideal gas, where mu naught is a function of temperature alone, and it is quite easy to see here. This can be considered of the form y equals sum m into x plus c, straight line equation. Therefore, if you plot y, which is mu here, versus ln p, which is x here, then you should get a straight line with this as the intercept. Therefore, the ideal gas is one whose chemical potential at constant temperature is a linear function of the logarithm, the natural logarithm, or whatever logarithm that one takes of its pressure. Then we started looking at non-ideal or real gases, which of course most gases are real or non-ideal, or in other words they do not follow the equation of state PV equals RT, and to describe them we brought in the variable fugacity, and in terms of the chemical potential that we have seen, fugacity can be given as mu equals mu naught plus RT ln F. This is for a real gas or all gases. When it is a real gas, it should also include ideal gases, or a real gas formulation should include an ideal gas formulation, and therefore mu equals mu naught plus RT ln F instead of RT ln P should be able to define all gases. That is what we said, and this is not complete without stating that F by P will tend to 1 as the pressure goes to 0. And therefore, it is quite easy to see under limiting conditions when F by P goes to 1, the fugacity is actually equal to the pressure. So, it is fine for ideal gases also. F by P we defined as something called a fugacity coefficient, which is unique to a particular pure substance. It is quite easy to realize that we need more mathematical, more accurate mathematical representations, because PV equals RT is not going to do the job anymore. And the first complication that we saw, or the first improvement that we saw in the equation of state to represent real gases is the Virial equation of state. It is to know what a Virial equation of state is, which is written in terms of what is called the compressibility factor. Compressibility factor is nothing but PV by RT. It is defined as PV by RT, and the Z is the one that is expressed in terms of a power series in P, and that is called a Virial expansion. For example, Z equals 1 plus B2P plus B3 P squared plus B4 P cubed plus B5 P power 4 and so on. This is a Virial expansion in pressure for the gas. Here B2, B3 are called the Virial coefficients, the second Virial coefficient B2, third Virial coefficient B3 and so on. And we also said that Virial coefficients are actually they represent the interactions between the molecules comprising the gas, and therefore they can actually be found from theory, statistical mechanics. For example, B2 represents interactions between molecules taken 2 at a time, B3 represents interactions between molecules taken 3 at a time, and so on. And also for low enough pressures, say about a few bar, just the first two or three terms of the Virial expansion is good enough to give an acceptably accurate representation of the gas behavior. But higher the pressure, more terms are needed to accurately represent the behavior. And we also saw that the Virial expansion can be written in terms of molar volumes. Of course, since it is a direct function of pressure, this has to be an inverse function of volume. Therefore, Z equals 1 plus C2 by V plus C3 by V squared plus C4 by V cubed plus C5 by V power 4 and so on and so forth. And C2, C3 can also be calculated from theory. We did an example where we looked at how to use the Virial equation to calculate some properties of interest. In this case, I think we did the volume of the vessel. We will not go through the example again. If you are interested, you can go back to the part of the lecture and look at it again. Since some of you may have looked at an iterative solution for the first time, let me just run through it again here. An iterative solution comes about when, especially when you have higher order equations, polynomial expressions. Here we had a cubic equation, therefore we set it up of the form, we had a Z equals 1 plus C2 by V plus C3 by V squared, but we knew that we were looking for V. Therefore, if we set up the equation such that you have a V on the left hand side and a V on the right hand side, you can do an iterative process to get at the solution. And to do that, we replaced Z by PV by RT, which is the definition of Z, and thus we got V on the left hand side and this on the right hand side. And to solve iteratively for V, the procedure was to guess a certain value of V and substitute it into the right hand side to find the value of the right hand side, then compare that value to the guessed value, or in other words take the difference. If the calculated value is close enough to the guessed value, close enough, as I said, was the operative word here, close enough to the guessed value, then the guessed value was the needed value. Otherwise, the calculated value is put back into the right hand side, rather it is used as the second guess, and that is put back into the right hand side to calculate a third value, then that is compared with the second value. This process is continued till a certain convergence, as it is called. In other words, the difference between the calculated value and the guessed value is small enough compared to the value of V itself, for example in this particular case. If it is less than, let us say, about 1 or 2%, it should be acceptable for most of our needs. These are the details of the solution, we will not get into that in the review. Okay, let me also mention this, that it is easiest to do these iterative calculations by using a program, and to write it in a form that can be converted into a program for easy calculations. We write it as Vn plus 1 equals RT by P into 1 plus C2 by Vn plus C3 by Vn squared. Therefore, V0 could be the guessed value, and V0 would result in V1, and then if V1 minus V0 is small enough, then we stop the iterations there. Otherwise, V1 is substituted here to get V2, then the comparison is made, and if it is small, if the error is small enough, the difference is small enough, we terminate it there, otherwise we keep going on. So, it is easy to write a program if we represent the equation in this form. And I think I will mention it here itself. It is the ideal gas volume is a good first guess value for the gas volume usually. And then we looked at cubic equations of state. Before that, we considered whatever we did till then. We said that we considered equations that describe the gas phase alone well, and then we looked at the rather we will be looking at cubic equation of state, which would represent both the gas and the liquid behavior reasonably well. And one of the cubic equations you may have already encountered in your higher secondaries class or in your first year courses, which is the van der Waals equation of state, which goes as P equals RT by V minus B minus A by V squared, and A and B are constants for a given pure substance. We said that the A and B can be calculated from critical pressure and critical temperature values. The okay, this might be worthwhile, so let me go here and recall our PV diagram here. PV, the variation between pressure and specific volume for a pure substance. Let us focus on this curve alone. There are very many parts to this diagram. In other words, these are pressure specific volume combinations, or specific volume pressure combinations where the different phases exist. We said under this dome you have the saturated phase, which is a mixture of liquid and vapor, and the top point of this is the critical point. Beyond this you have critical behavior, where the properties are very different. We said that we are not going to look at the properties of the critical phase in this particular course. So, this is the critical point, just to recall. And from that critical point, which is tabulated for pure substances, and that tabulation is available in the appendix of your textbook, we could get the values of A and B by these expressions. A was 27 R squared Tc squared by 64 Pc, and B equals RTC by 8 Pc. This is for the van der Waals equation of state. Then another popular cubic equation of state we saw as the Redlich-Kwong equation of state, which is given as P equals RT by V minus B minus of A by T power 0.5 V into V plus B. And we said the A and B in the Redlich-Kwong equation of state can also be calculated from the critical properties. A is given by 0.42748 R squared Tc power 2.5 by Pc, whereas B was 0.08664 RTC by Pc. Then we also saw the basis for writing these A and B values in terms of TC, PC and so on, we have equivalent expressions for the van der Waals equation of state also, and this was given as a homework, and the basis for that is as follows. Let us go back to our P versus V diagram again. If you look at this point here, at this point you have a 0 slope, the slope changes sign. Therefore, dou P dou V, this is at a particular temperature, therefore dou P dou V at constant temperature equals 0 at the critical point. Not just that, the sign, it is also an inflection point, which means if you look at the derivative, the sign of the derivative also changes at this point, and therefore this becomes an inflection point, and therefore the second derivative dou squared P by dou V squared also becomes 0. We said we could use these two criteria or these two relationships that have been become apparent to calculate the A and B values in terms of the critical constants. And this is actually available in your textbook chapter 3, if you want you can look at that. And then we went to the estimation of volumes using the equations of state. We said that the Redlich-Kwong equation can be used to estimate volumes of pure component, and since it is a cubic equation we need an iterative solution. The initial guess of course is important and so on. We said, yeah, the good initial guess for vapor volumes is through the ideal gas equation. A good initial guess for the liquid volumes is from the constant B, because remember that V minus B term either in the van der Waals equation or in the Redlich-Kwong equation of state. Therefore, that gives you an idea that B represents the volume that is occupied by the molecules. When it is a gas, the molecules are farther apart, and therefore the fraction of volume that is occupied by the molecules is less, whereas in a liquid they are all close together, and this value of B could be the first guess that one could make when one is looking at liquid volumes. It is quite easy to see that you put all the molecules together and you choose the total volume of the molecules, that should give you some value of the volume in the ballpark of the liquid volume. That is the idea with which these are chosen. And to set up the Redlich-Kwong equation for the iterations itself, we went through a strategy. We multiplied the Redlich-Kwong equation by V minus B by P to get it of this form, and to facilitate for vapor volumes we had written it as RT by P plus B minus A into Vn minus B divided by square root of T into P into Vn by Vn plus B. Therefore, you could do iterations with this for the vapor volumes, whereas we have a problem if we consider the same form to do liquid volumes. Why? We said our initial guess was going to be B, and if our initial guess is going to be B, you substitute it here, this entire term will go to 0. Therefore, we lose the information that is given by this term altogether, and maybe either the values that we get will not be realistic or they may not be convergence at all. Therefore, we need another form of the Redlich-Kwong equation to estimate liquid volumes, and that was obtained by writing the Redlich-Kwong equation, expanding, multiplying, taking out common terms, multiplying, cross multiplying, and representing it as a polynomial expression in V. So, that was V cubed minus RT by P by V square into V squared minus B squared plus B by B RT by P minus A P T power 0.5 into V minus AB P T power 0.5 equals 0. So, this does not pose the problem of any term vanishing completely and thereby not contributing to the solution or a meaningful solution of the volume. So, this form can be used to iterate for liquid volumes, and to do that iteration we had to transpose that equation as Vn plus 1 equals b squared plus b RT by P minus A by P T power 0.5. This, remember, this was in the numerator here, so this has to be in the denominator on the other side. In other words, we are dividing both sides by this to get rid of the term here, therefore this is to the power of minus 1 into the remaining terms that was there in the previous equation, Vn cubed minus RT by P Vn squared minus AB by P T power 0.5. We again worked out an example where we had used the Redlich-Kwong equation to estimate the volumes of the saturated vapor and the saturated liquid of a very popular biological substance, ethanol. Okay. Then we said that we had seen ideal gas law, the equation of state applicable only to ideal gases, the Virial equations that were applicable to a wider variety of gases, and cubic equations that are applicable either to a gas or the liquid states of the pure substance. And then we said that we are going to come up with a formulation that is applicable to almost all gases. So this part of the module focused on the PVT relationships in increasing degree of generality in a certain sense. In ideal gas law, a very narrow range of application, Virial equations, a very wide variety of gases from some small number of gases. Then cubic equations could do both gas and a liquid, and the generalized formulation could do a larger variety of gases with lower input. Essentially the data that you need is only the critical constants, you do not need pure substance specific constants. That is the advantage while using generalized correlations, as we had seen. We will see that again here. So the generalized correlations are written in terms of the reduced properties, and the reduced property was nothing but the ratio of the property to its critical value. For example, reduced pressure was PR, which is defined as P by the critical pressure Pc. Similarly, reduced temperature and the reduced molar volume. And to write the Redlich-Kwong equation in a generalized form, we did some manipulations to get it of this form. Z equals 1 by 1 minus H minus A by B RT per 1.5 into H by 1 plus H, where H was just a convenient combination of B by V, which can also be written as Bp by ZRT. And then we could express A and B in terms of the critical constants that we have already seen earlier, and therefore if you substitute those expressions here for A by A and B, then which are these we had already seen, then the generalized Redlich-Kwong expression turns out to be Z equals 1 by 1 minus H minus 4.934 divided by TR per 1.5 into H by 1 plus H. So that is the Redlich-Kwong equation written in terms of reduced properties. The advantage here is that you have only TR, the reduced temperature, and H of course is given in terms of PR and TR. So PR and TR relationships would be applicable in general, and therefore this expression's applicability becomes a lot more general. Not just that, any equation of state can be written in terms of the reduced form or the generalized form if it is written in terms of the compressibility factor and reduced properties. And to re-emphasize, the only data that is needed when we use the generalized equation of state are the critical properties that are readily available, for example in the appendix of your textbook. So then we looked at a slightly abstract concept, which was the two parameter theorem. Now theorem has a lot of power to it, you have tremendous confidence when you have it in a theorem form, you could apply it in many different situations, and the above development in fact was formalized into a 2 parameter theorem, which said that all fluids have approximately the same compressibility factor when compared to the same reduced temperature and pressure. In other words, they all deviate from the ideal gas behavior by the same extent. It was found that the 2 parameter theorem's applicability was somewhat limited. It could give good results for simple fluids, whereas there were significant deviations for many other fluids. To account for that, Pitzer and co-workers brought in the eccentric factor, which was essentially, I will not go through the development here, you can look at the notes or the presentation, these slides in the presentation later. The eccentric factor is essentially the difference between the logarithm of the PR sat value at a TR value of 0.7 and that value for simple fluids, which happens to be -1. Therefore, this in essence gives the deviation from the simple fluid behavior of the other fluids, and therefore this is taken as a single parameter. And this also is attractive because it involves only one measurement at TR equals 0.7, the vapor pressure. So it is a very simple measurement to find out the eccentric factor. We do not have to do all that. The values of the eccentric factors of most substances that we would need is available in tables. Of course, one, if and when one needs to generate that data, then you know how to, the basis for generating that data. And this led to the 3 parameter theorem of corresponding states, which said that all fluids with the same value of the eccentric factor have the same compressibility factor when compared to the same reduced temperature and pressure. In other words, they all deviate from the ideal gas behavior to the same extent. This was applicable to a wide variety of gases, and the kind of equation of state that can be written in terms of that can be a consequence of the 3 parameter theorem is Z equals Z0 plus omega times Z1, and it so happens that the value of Z0 and Z1 are available in tables. In fact, that is the reason why we write it of this form, so that we can, rather it was we would use this form as written here because the values are available to us. They work well for most cases when we use the Z equals Z0 plus omega times Z1 formulation. The predictions are within 3% of the experimental value for non-polar and slightly polar gases. Well, they do not work as well for highly polar gases or gases that associate or quantum gases such as hydrogen, helium and neon. You could also get liquid properties from the generalized correlation. Nevertheless, the importance that one would associate to those values are need to be a little less. The values are approximate, the liquid values are approximate, the gas values are very good. Apart from the tables, there are analytical expressions for Z0 and Z1 that are also available. If the table is not available to somebody, one can use these expressions, which are reasonably accurate. Z0 is given in terms of V0, the virial coefficient, and V0 is given in terms of TR. B0 and B1 are given in terms of TR. Then we worked out an example where we applied the generalized correlation and also compared it with the ideal gas and the virial correlations, so the values obtained from those. So that was one major part of the module. Then we went into the second major part of the module, which was estimation of the other thermodynamic properties, or more difficult to measure thermodynamic properties in terms of PVT. For that we needed a formulation, and that formulation required what are called residual properties. Residual property is nothing but the difference between the actual value and the ideal gas value. For example, the residual volume Vr is nothing but the actual volume minus the ideal gas volume, which was written in terms of the compressibility factor for ease of use. It will turn out to be RT by P into Z minus 1, and then we said that we could write any the residual property for any extensive thermodynamic property. You could write one for internal energy, for entropy, enthalpy, Helmholtz free energy or Gibbs free energy, and if that is represented as Mr, the residual property is M, the actual property minus the ideal gas property. And then we showed why G by RT is considered the generating function, or G is considered the generating function, because if we have the value of G, you could get other values. Please go through this derivation again, it might be interesting. Here, if we have G by RT, V by RT is nothing but dou P of G by RT at constant temperature. H by RT was nothing but minus T dou T of G by RT at constant pressure, and also U by RT was H by RT minus PV by RT, and S by R equals H by RT minus G by RT. We are not looking at A because we may not need it extensively in this course, but of course you could write A too, this is not a problem. Then we went and saw how to write residual properties. This was a derivation, I am not going to go through that. Yeah, the Vr by RT, you could write it in the same fashion as earlier. Earlier it was for the actual values, here you could write it for the residual values. Vr by RT equals dou P of Gr by RT at constant temperature. Hr by RT was minus T dou T of Gr by RT at constant pressure, and then we said that we had assumed constant temperature, but we got it in terms of values. Yeah, Gr by RT is in terms of Vr, still Vr by RT dP, this is good, but we wanted an easier way of estimating that, therefore we wrote it in terms of Z. Yep, Gr by RT equals integral of P reference to P2 Z minus 1 dP by P. Okay, this makes it easily evaluatable, and we said that the value of P reference is usually taken as 0. Then we had expressions for the other thermodynamic residual properties in terms of measurable properties, this we have already seen. While deriving this, we went through a situation where we needed to differentiate an integral. For doing that, we used the generalized Leibniz rule, which gave us a means to differentiate or partially differentiate a definite integral. Here, so after doing all that, we ended up with Hr by RT equals minus T integral of P reference to P2 dou T of Z at constant P into 1 by P dP. And then we also noted that although the state variable values will not change with the path chosen, the experiments that are designed to evaluate these are path dependent, they need to be performed along a path, and therefore we need appropriate conditions, experimental conditions, or appropriate mathematical expressions. Then these are the other residual properties in terms of Gr by RT and other things that we know, and in terms of the easily measurable values, Sr by R was minus T integral of P reference to P2 dou T of Z at constant P into 1 by P dP minus integral of P reference to P2 Z minus 1 dP by P. And we said that this is quite obvious. Once you have the residual value, the actual value is nothing but the residual value plus the ideal gas value. Therefore, if you have the ideal gas value, then you could find the actual value, or for a process when you are going between points or states 1 and 2, m2 by minus m1 or delta m equals delta mr plus delta m ideal gas. We also noted that the thermodynamic properties of state functions, thus the experimental conditions employed, say constant temperature, are irrelevant to the actual values. The values depend only on the state and not on the path followed or the experimental conditions employed between the states, but also note that the values are with respect to a particular reference state and must be explicitly defined. Then we came up with ways to get the ideal gas values, because we said the residual value plus the ideal gas value is the actual value. We spent a good amount of time getting the residual value first, and then we looked at how to get the ideal gas values. Without spending too much time here, we had derived all these. Yeah, this was the expression. ds was Cp ideal gas dt by T minus R by P dP. Therefore, by integrating that you could get the ideal gas value for S, and for process values between point 1 and 2, the differences in values. We first wrote them and then wrote them in terms of the easily measurable PVT and a few others, Cp and so on. Delta H was integral of T1 to T2 Cp ideal gas dt plus H2R minus H1R, and delta S was T1 integral of T1 to T2 Cp ideal gas dt by T minus R ln P2 by P1 plus S2R minus S1R. We said that the above equations for the other thermodynamic properties can also be written in terms of the reduced properties. We had looked at only 2 or 3, and the reduced properties, when the reduced properties are used, the equations become generalized, they become applicable to say all gases, and therefore we need not look at specific PVT data to estimate thermodynamic properties. That was the advantage that we saw. There are generalized correlations for residual properties also, and the advantage that we just mentioned, we went ahead and derived those generalized correlations. And let me just present these generalized correlations. These were the correlations in terms of the actual properties, and we had substituted to get equations 347, 348 and 349 in terms of reduced properties. Gr by RT CTR was integral of PR reference to PR2 Z minus 1 dPr by PR. HR by RTC was minus TR squared integral of PR reference to PR2 dou TR of Z at constant PR dPr by PR, and SR by R was minus TR integral of PR reference to PR2 dou TR of Z at constant PR dPr by PR minus PR integral of PR reference to PR2 Z minus 1 dPr by PR. And the same way that we took P reference as 0, we also take PR reference as 0 for as the lower limit of integration. We said that we could write these equations in the generalized form also in terms of Z0 and Z1, because then we can use the tables that are available to us, and the explicit form is HR by RTC was HR0 by RTC plus omega times HR1 by RTC, and SR by R was SR0 by R plus omega times SR1 by R, and the values are available, the groups, the 0 group and the 1 group, the values are available in tables E5 to E12 in appendix E of your textbook. And then we worked out an example to look at how to use the correlation, the generalized correlation in terms of the reduced properties to get at useful values. Please take a look at that whenever you have the time. The last thing that we saw was the estimation of the fugacity coefficient for a pure substance, and to do that We started out with the definition of the chemical potential for a species. We went into the interpretations of the chemical potential. Please take a look at it, it is very interesting. I will not do it again now. And we went into writing the definition for a pure substance, and writing down equations for a closed system in terms of the chemical potential for a pure substance. Then we went ahead with the derivation, to get to this particular expression, which is the penultimate expression, ln of Phi1, this is the Fugacity coefficient at point 1, is the integral from 0 to P1 V by RT minus 1 by P dP, and in terms of the compressibility factor, this can be written as integral of 0 to P1 Z minus 1 by P dP. And since we know so many ways to get at the Z value that we have seen so far in the module, we could use all those methods here to get also at the Phi1 value. And then we worked out this example. This example was a slightly more complicated one in terms of needing slightly higher level skills of integration, which we saw not very difficult, but only that it needs a higher level skill from what was required to solve the previous set of problems. And we went through solving the problem to get at the Fugacity coefficient of isopropanol. So that was all that we did in module 3. When we start the next class, we will start with module 4 and look at solutions. This was pure substance, we mix pure substances together, we get solutions, and we look at properties of solutions. See you then.